Thanks a lot, Matthias. So I will not give a very historic overview. I apologize for that. So I think Monin-Obukhov similarity theory, I don't really have to talk a lot about why it is important or what are the main points of why we use it. And I think it's one of the most celebrated theories that actually came over the past 100 years. And we find it implemented pretty much everywhere in all the weather models, even LES. We use Monin-Obukhov similarity theory, and it's also served so far as a cornerstone of our understanding of surface layer turbulence. And so, of course, to you, I don't really have to say what is the point of Monin-Obukhov similarity theory, but we have the universal behavior of turbulence that is only governed by the distance from the surface and by the Obukhov length, or by the stability parameter. So any properly non-dimensionalized mean quantity is some universal function of Z over L. And this is, of course, the most famous figure maybe that is most used, that comes out of Monin-Obukhov similarity theory, that is the phi m, or the wind speed profile. And yeah, I'm sorry, my slides are not very well organized. Okay, so we have the phi functions that we know that we use everywhere. Now, the problem with Monin-Obukhov similarity is that it was developed for stationary turbulence in flat and horizontal homogeneous terrain with no subsidence, and under the assumption that fluxes do not vary with height. So we define the surface layer. And as you can imagine, that already poses a lot of problems with, if you think of all of your research, a lot of these assumptions are violated. But implicitly, there are additional assumptions in Monin-Obukhov similarity theory, and that is that turbulence is always locally generated, that we only have one scale, and that is the vertical scale. So there is no horizontal scale, there's no possibility of having additional scales to govern the problems. And then also that the energy containing eddies are actually the size of height Z, which is why Z over L is the relevant parameter. So as was already mentioned before, order out of chaos, Monin-Obukhov doesn't include a number of important processes. For example, it does not include the self-organization of turbulence. And here, oops. Yeah, okay. So here you have the formation of convective cells or convective rolls. This is just like LES. And you can obviously see that in convective conditions, turbulence tends to self-organize, and that is not included in Monin-Obukhov similarity theory. But in addition to that, we also are missing a number of other length scales that we know are potentially important. So for example, the mixed layer height, we will see very soon. It was found out quite early on that mixed layer height will have an impact on the near surface turbulence when we talk about horizontal variances. But then there are also additional heights, such as, for example, the low-level jet height that is especially relevant in stable conditions when we have low-level jets, or on slopes when we have katabatic flows. And the jet height might be actually smaller than the Obukhov length, and therefore a more relevant length scale. Additional scales that are not included are, for example, scales of heterogeneity, and we know that Earth is not really homogeneous. We will have later today a session on stratified turbulence, and obviously if you go to very stable conditions, turbulence is not well developed. We can have intermittent conditions, which is obviously non-stationary. We also have other non-stationary forcings, such as sub-mesoscale motions that clearly violate Monin-Obukhov similarity theory, and that are also that are happening in the energy gap that we assume is valid if we want to do Reynolds averaging. So the lack of a spectral gap makes it very difficult to understand what is turbulence and what is not turbulence in very stable conditions. And then if you look outside of the window, you will see that the world is mostly not really flat, or the surface of the Earth is not really flat. So about 70% of the Earth's land surface can be classified as complex terrain. And we can argue what it means, complex terrain, whether it's hills or whether it's mountains that you see outside. But once we start measuring turbulence in conditions that are no longer flat, such as, for example, A-heads here or Cabal, which is pretty flat. When we go into more complex conditions, and this is one of our mountaintop sites, we see that fluxes are not constantly at height. We cannot observe a constant flux layer, and obvious additional effects that are not included in Monin-Obukhov are relevant, such as, for example, with heterogeneity, we know that there should be an advection, terrain-induced pressure perturbations, or pressure transport, streamline curvature, etc. So this is all what we know now that poses a problem for Monin-Obukhov, yet Monin-Obukhov is still used pretty much everywhere in all conditions for lack of a better theory. But already pretty early on, actually, it was known that there are challenges for Monin-Obukhov similarity theory. And one of the first ones was the non-scaling of horizontal velocity variances in convective conditions. So here, actually, these are the data from A-hats from very flat terrain data set. You have the vertical velocity variance scaled as a function of zeta. And you can see that it really nicely collapses on a line, and we are really happy and say, okay, Monin-Obukhov is really good. And then if you plot the data from horizontal velocity variances, then they're all over the place. And it was known already quite early on. So in the 60s, just a couple of years after the sonic anemometer was invented, that then Monin-Obukhov does not explain the horizontal velocity variances. The other thing that was also recognized quite early on is that the spectra do not scale either in convective conditions. So this is from Kaimal. We have the scaled spectra of the horizontal velocity components, and they scale really nicely as a function of Z over L until you reach unstable stratification, and all of a sudden there's a shaded region where there is no excluded region where there are no scaling relations. And then if we go to complex terrain and we do the same exercise, we plot some kind of a scaled function. So here it's the wind shear, vertical wind shear, and vertical temperature gradient as a function of Z over L. So this is unstable, this is stable. I'm sorry, the points are a bit transparent, okay? But you can see that there's some large shading, and then there are a couple of curves, and they're like not on top of each other, especially in the very stable conditions. Even the literature curves are not really agreeing on what is happening. And then for horizontal velocity variance, for the horizontal, vertical, and temperature variance, these are the different data sets. You can see that there's quite a large scatter between the data sets. So each data set pretty much suggests its own scaling curve, which is not really useful for anybody because that we cannot actually parameterize. Okay, so the question really is, there's so many limitations to the applicability of Monin-Obukhov. Should we just give up? And maybe we need to find something better, something new. Maybe we need a new, fresh look at turbulence. And so it would be great if we could have a discussion about that. Maybe machine learning, maybe, I don't know, just why bother with Monin-Obukhov? It was great when it was founded, but okay, maybe it's time to move on. Well, of course, my topic and my project is on Monin-Obukhov, so obviously my answer is no. We can rescue Monin-Obukhov. There is a way of making it work also in conditions for which it was not developed. And some of the early amendments to the theory already, I mean, they're no longer Monin-Obukhov, but it's not like they are totally opposite. So the scaling approach still works. So the first one was mixed layer scaling for horizontal velocity variances, where they recognized that due to the large convective eddies that span the entire boundary layer height, horizontal velocity variances are actually scaled with the ZI, so the CVL height, mixed layer height. Here, and you can see, this is a figure from before with Monin-Obukhov, and here the scatter is much better. So, okay, there is some hope. Then the other advance that was made a bit later was the local scaling approach from Newstad, which allowed Monin-Obukhov to be kind of extended to the entire stable boundary layer instead of only being valid for the surface layer. And this is what we can see will also help us in complex terrain. But already really early on, one of the basic assumptions that there is only one vertical scale and there is no horizontal scale was questioned. Okay, so Zemletikiewicz actually, Sergei, already in 1971, proposed that actually we need to have an additional horizontal scale and not just a vertical scale, the Obukhov length. And then Bechov and Yaglom in the same year pretty much picked up this idea, and then they used directional dimensional analysis with two horizontal scales, and they tried to reproduce the, this is the wind shear, so this is phi m function, and phi h function, so for the temperature and the wind speed profile in unstable conditions, we should actually be minus zeta. They recognize that there are three scaling regions. There's a dynamic layer, a dynamic convective, and a convective layer. And so that actually they have different scaling conditions because in some of them, the horizontal scale is more important than the vertical. But they also use the assumption that the horizontal and vertical velocity scales are decoupled. Now, following on that idea that there has to be some level of anisotropy accounted for in the system, Tom and Guyan also developed the multi-point Monin-Obukhov, which said, okay, we do know that there are two length scales, or that the horizontal scale is also important, but we do not want to assume that the vertical and horizontal velocity scales are decoupled, because that's not true. And so the only way that they could incorporate the horizontal scale was through multi-point statistics. So for example, the spectra. And so they have a horizontal scale, which is k, the streamwise wave number, and then the vertical scale. And they said that both have to be normalized by the Obukhov length. So the Obukhov length is actually also the relevant length scale in the horizontal, not just the vertical. And so with a lot of mathematical input, they developed their own scaling regions, and they again identify the dynamic and convective dynamic region, and then they propose the different slopes of the curves of the spectra. So this is spectral scaling. Okay, so now I kind of come to my work a little bit. So obviously this anisotropy, the importance of anisotropy was recognized really early on. But the way it was implemented was different. So there are different approaches, either the one from Zemletikiewicz or the one from Tong and Yuan. But at the same time, Langley did really important work in the 70s, where he recognized from looking at the Reynolds stress tensor and tensor analysis that he can actually account for anisotropy with two variables, two scalar variables, or two invariants of this Reynolds stress tensor, which I'm calling here XB and YB based on the work of Banerjee. So pretty much all of the realizable states of turbulence fall within a triangular region that's defined by this XB and YB. And because it's a triangle, it has three limiting states on the vertices. So we can have isotropic turbulence at the top, two component axis symmetric at the bottom, and one component here, and that these names refer to the eigenvalues. So we can actually think of it this way. If we have isotropic turbulence, then all the three eigenvalues are the same. If we have two components, then two are larger than one, and if we have one component, then one is larger than the two. So this is just a way to kind of sort turbulence into different categories. And we know actually under which conditions we can expect different types of anisotropy. So for example, isotropic turbulence, we know from Kolmogorov, should only occur in the inertia subrange. And two component is really often found in shear driven conditions where we have one dominant length scale that's caused by the shear. And one would expect that in purely buoyancy driven conditions, when the vertical scale caused by buoyancy is the dominant one, we will have one component turbulence. But actually in some of the research we can show that in these kind of conditions, we actually have quite pure, almost quasi-isotropic turbulence. So in very convective conditions, a bit away from the surface, one has almost isotropic turbulence. And there, like for example, one component turbulence is only found in waves meandering counter gradient fluxes. So this is research that really is ongoing to understand when the turbulence have which type of anisotropy, but it turns out that how you get to anisotropy is not as relevant as which anisotropy ultimately have. Okay, so I don't care if I got two components with shear or in stable conditions with, I don't know, something else. What will be important is just that it has a specific type of anisotropy. And why is it important? Well, actually, if you remember, the horizontal velocity variance is scaled. So phi u, it had this huge scatter. But if we now filter it, if we cluster it according to the anisotropy, and here the anisotropy is just the variable, the invariant yb, which tells you, are you very isotropic or are you very anisotropic? If we cluster it, we see that this scatter really is due to mixing different types of anisotropy. And so we can take this to develop new scaling relations, because obviously it looks like zeta is an important parameter, but there's another important variable that we are not taking into account. So we can develop new scaling relations that include anisotropy, and it turns out that the way anisotropy enters into the classical Monin-Obukhov is through the constants. So what is a constant in Monin-Obukhov is actually a function of anisotropy, if we want to generalize it. And so what does it look like? So these are the horizontal velocity variances. This is the vertical one for unstable stratification, and for stable, and the full lines are the classical Monin-Obukhov curves. Okay, so you can see that in some conditions there is no influence of anisotropy, but for some variables there is a strong influence. For example, for the vertical velocity variance in stable conditions. And so if we include anisotropy, this is what we get. Okay, so you can see that we can actually get a really, really good collapse of data onto a scaling curve. And that's what we usually assume means successful scaling. Okay, so you can wonder, what about mixed layer scaling? Because mixed layer scaling was a solution to the scaling of horizontal velocity variances. And now I'm plotting the same figure as before, but now colored according to anisotropy. So this is what normal Monin-Obukhov looks like, and you see this nice separation according to the color. This is mixed layer scaling, which also has a bit of separation according to the color. And this is if we include anisotropy directly. So obviously, anisotropy has to somehow incorporate the effect of the mixed layer height. Okay, well, what about other variables? We can also show that it works for the temperature variance, for example. Again, what are constants are actually functions of anisotropy. The function form is a bit complicated, but it doesn't matter. And we can see this is the temperature variance in stable conditions. Because it's such a nonlinear influence, we can actually define families of curves that go through the different clusters. But what is interesting here is what brings me back to Sergei's work. If we know these are now vertical velocity variance and the temperature variance in stable conditions scaled, and here we are in very stable conditions, and you can see that they have opposite behavior. So if turbulence is quasi-isotropic, which is this blue value here, then vertical variance is high and the temperature variance is small. And if it's very anisotropic, the vertical variance is small and the temperature variance is large. And if you know the work of Sergei, then you know the concept of total turbulent energy, which is the sum of the TKE and the TPE, TPE being the turbulent potential energy. And it's actually defined through the temperature variance. So what we can see here is that this coupling between TKE and TPE is really, that anisotropy is really important for that. And it's over a range of zeta. So it's not like that the stability function itself describes this. There is an additional element of anisotropy. Okay, now another problem we saw with Monin-Obukhov was the non-scaling of the spectra. And so this is the original chimal region with excluded region. Well, this is actually the work of Claudine. What we can see that if we take now the data from this excluded region and we cluster it according to anisotropy, well, they just like really nicely separate. Okay, so that means it's not wonder, because if the horizontal velocity variances are explained by anisotropy, then also the spectra, which is like the opposite of that, should be explained. So we can see that the anisotropy of turbulence really explains why these unstable horizontal velocity variances or spectra are not scaling. Now, this is all relatively fine, but what about the one that we really are interested in, which is the vertical wind shear and temperature gradients? So this is the work of Samuel and Mosso. So this is phi m for unstable and stable stratification. We can see that in these very convective conditions, we definitely have a large influence of anisotropy. So for very unstable conditions away from the surface, we have almost isotropic turbulence, and it has much smaller gradients for the same U star than very anisotropic turbulence. And for the temperature gradients, it's even stronger. We see that the data are really pretty much parallel, but they're really strongly dependent on anisotropy. Now, this is from the data. We can actually show something very similar from LES. So this is an LES over homogeneously heated flat surface. And what you can see here is pretty much phi m as a function of zeta in unstable conditions, the same color scale. So you can see that this separation according to anisotropy is also visible in the LES data. Okay, now I think that really accounting for anisotropy is really important to make Monin-Obukhov more generalizable. We are still stuck with knowing when do we have which type of anisotropy. But this approach does not solve one of the large problems in very stable conditions, and that is non-stationary motions and intermittency. So Nikki Verkautrinen and her student, they actually worked on a stochastic treatment of this type of turbulence. So this is, again, phi, and they have a stability correction, which they develop as a stochastic approach. With stochastic approach, they show promise that this kind of stochastic approach might be used to parameterize this very non-stationary intermittent turbulence in very stable conditions. Okay, so to conclude, I still think that there is hope for Monin-Obukhov. We need to tweak it a little bit. We need to work on it to make it work, also over complex terrain. And I think in that process, we need to include anisotropy, whether it's through this YB or some other form. I cannot say really. I would say use the invariants that Lumley developed. But what this also shows, and maybe we could talk about it, I couldn't show everything, is anisotropy really, the fact that it scales means that anisotropy has to encode all of the non-local effects and the complexity of the turbulent of the boundary conditions, because this approach can make it work also over complex terrain. At the same time, I think that stochastic approaches are still very relevant to address the non-stationary, very stable conditions. And I think that that would be also a nice thing to discuss in the groups. Okay, and with that, thank you very much.